So in this problem, we're doing a cosmic ray experiment. In a cosmic ray experiment, particles with a charge of magnitude 3e, where e is the charge on a proton, and a mass of 6 times the mass of the proton, where the mass of the proton is 1.67 times 10 to the minus 27 kilograms, enter a magnetic field of 0.25 Tesla and are bent as shown into a circle of diameter 0.95 meters. And so if we fill out some of this stuff, we can kind of see, right, this is my Q here, right, or at least the magnitude of Q. Q could be positive or negative, right? There's my mass. This is my B, 0.25 Tesla, and my radius over here, which is the radius on the circle, is 0.475 meters, something like that, right? And so this is the problem we've solved with objects in circular motion, charges in circular motion in uniform magnetic fields, and we already did this, and we got so you know, the sum of the forces is equal to the mass times the acceleration, and we got, for the forces, we got Q V B sine theta, and that's equal to mv squared over r. I'm using a capital R this time, right? Since the velocity is this way and the magnetic field is up, right? My magnetic field here is B. That's the thing that's pointing up because that's what the dots mean. Then this guy here is just 1 because it's the sine of 90 degrees. And so I get QVB equals mv squared over r. And so this is whatever questions I have to answer, I'm going to need to use this one. And so they're asking, part A asks me, what is the velocity? Right, and so I can solve this for the velocity. I get the velocity, if you solve it, is QBR divided by the mass. If you rearrange, you cancel a V on both sides, you multiply through by the R, and you divide by the mass. And what that gives me is 3 times 1.6 times 10 to the minus 19th coulombs. So that's the charge, right? It's 3e times the magnetic field, which is 0.25 Tesla, and times the radius, which is 0.475 meters, all divided by the mass, which is 6 times 1.67 times 10 to the negative 27 kilograms. And if you evaluate that, you get V equals, or what I get is 2.8 times 10 to the 6th meters per second. So a high velocity. So that's how fast they're going. Now, one of the things about this experiment, which we were doing with electric charges also, is we were saying, I'll erase this part of it. You can go back to it. Part B says, is it okay to neglect gravity, right? If these are cosmic rays coming down from space, maybe this is the downward direction, I don't know. But the question is, what is the force of gravity acting on these particles? And that's just mg, which is just 6 times the mass of the proton, times g, which is 6 times 1.67 times 10 to the negative 27 kilograms, times 9.8 meters per second squared. And if you evaluate all that, you get about 2 times 10 to the minus 25th newtons. And the question is, how does that compare to the magnetic force, which is QVB? Right, and now that we've got the V, we can evaluate this. And this is, the Q is 3 times 1.67 1.6, I'm getting there, times 10 to the minus 19th coulombs times the speed which we got for it just a second ago, which was 2.8 times 10 to the 6th meters per second times 0.25 Tesla. And so since both of these use all SI units, I can just multiply by through and I get about 3.4 times 10 to the minus 13 newtons. And so you can see the gravitational force is more than 10 orders of magnitude less than the magnetic force, and that's gravity doesn't show up. It's even worse for the electrical force, which we calculated a few times. But the magnetic force is way stronger on these individual charges in typical situations. So one more question, I guess, or maybe two. Question is, what is the sign on a charge? Is it positive or negative? And well, the way we answer that is by looking at the right-hand rule. And if I was going to figure out how this charge went, I would say, well, I would put my arm along the velocity for the right-hand rule, and I curl my fingers towards the magnetic field this way, and so I would get a charge, a velocity in that, a force in that direction. Let me go from this direction, right? If I was going to put my arm along the velocity and curl my fingers towards the magnetic field, I would get it this way for a positive charge. But since the picture tells me it went this way, I know that the force is in this direction, so that means the charge was negative. And so the answer is Q is minus 3e. I could say D The last one is, how does the speed of the charge change as it moves through this circle, right? And the answer is, see if you can guess the answer, pause it or something. The force is always perpendicular to the velocity, right? That's how this magnetic field force works. At least when the magnetic field and the velocity are perpendicular, the force comes out perpendicular. And so the velocity does not change. So, sorry, the speed does not change. The speed doesn't change. It's the direction changes, so the velocity is constantly changing, but the speed is not changing.